Welcome everybody for this last lecture of this QGP class, and the lecture will be devoted to heavy flavor production in high energy nuclei collisions of nuclei. And so this is the outline of the lecture. I will start by reminding you something about heavy flavor production in elementary collision. With elementary I mean let us say proton-proton collisions, even if protons are not elementary objects. Then I will move to heavy ion collisions and display why heavy flavor are important as a tool to understand the parton-medium interaction, and in particular to perform, once we have a correct description of this parton-medium interaction, to perform a tomography of the matter that we have produced in this kind of collisions, in particular to understand the temperature, the energy density, the transport coefficients of the medium. And the tool that we will use to do this will be an equation which is called the relativistic Langevin equation, which is, as we will see, a kind of transport equation. So let us start from heavy flavor production within perturbative QCD. So the idea is the following. Charm and beauty have a large mass, and this makes perturbative calculation possible due to the number of reasons. First of all, because the mass sets a minimal of shellness of the intermediate propagators so that the diagrams don't diverge. It sets also a hard scale for the evaluation of the strong coupling, so this alpha S is sufficiently small so that the convergence of the series is quite fast, and it prevents collinear singularity by suppressing the emission of small angle gluons, and this makes calculation at the partonic level well defined. I will show you in a moment why. So, as yesterday we saw that once you have a hard process in which you produce a high energy parton, this parton in general can radiate gluon, and we evaluated the probability of radiation of gluons, and we saw that it is characterized by a soft and a collinear divergence. So that I mean, calculations at the partonic level are not so well defined because of this you can say that it will in general cancel if you do things properly with some virtual correction in higher order calculations, but you are left with this collinear singularity that you must somehow regularize. And what you do is to introduce a sort of intermediate, let us say, cutoff, which is called the factorization scale, and which allows you to do calculation in a well-defined way at the level of hadrons. So you establish this intermediate cutoff, and you say that, well, what I measure at the end are not partons but hadrons, and so I convolute the partonic calculation with a fragmentation function, which tells me the probability of going from parton F to hadron H, in which essentially the dependence of this fragmentation function on this factorization scale, so its evolution with the factorization scale, compensate the dependence of the factorization scale in the partonic cross-section. At the end, the final observable is well defined. Well, if you do the same in the case of a massive quark, the fact that the quark is massive introduces a modification in the formula that we saw before, and you see that the presence of this mass in the propagator suppresses the radiation of gluon at small angles, and so that already at the partonic level, at the level of quarks, heavy flavor production is well defined. So you can then calculate the production cross-section in elementary PQCD processes in terms of Feynman diagram. At the tree level, you have just these diagrams, and you see that in these propagators, the mass of the heavy quark introduce a minimal of shellness. Then, of course, alpha S is not so small, so you had to go beyond the leading orders, and you must also consider next to leading order corrections. And these next to leading order corrections are of two kinds. Yeah, first correction coming from this real emission, in which you can radiate a hard gluon, sufficiently hard gluon, and then, but at the same order, alpha S cube, you have also a contribution coming from the interference between these virtual diagrams, in which in the final state you have still only two partons with the tree level amplitude. Okay, you sum and you get a result at the next to leading order accuracy, alpha S cube, both for the total cross section and for the single particle inclusive spectrum. Okay, a calculation of this kind can be also implemented in an event generator like POWEG, MCTNLO, which really produce a list of hard events. And as I show here, you can also interface the result of this event generator for the hard event with a parton shower. So essentially, you simulate within such kind of setup both the hard process, in which we have a 2-2-2 or 2-2-3 process, in which you produce sufficiently hard partons in the final state. Interface it with some other automated tools like Putty or Ervik, which take care of also simulating the radiation of soft collinear gluons in the shower, and also other possible non-perturbative effects, like an intrinsic KT of this incoming parton, which are not perfectly collinear, like multi-parton interaction, in the sense that in a single proton-proton collision you can have multiple semi-hard 2-to-2 scatterings, and also you at the end these tools can also simulate hadronization, so the transition from partons to hadrons. And they provide a fully exclusive information on the final state. So for each event, you have really a list of particles in the final state, and not only of the particle, but also of the parents of these particles, of the grandparents, and so on. Okay, so it's a tool which provides you quite a list, quite a rich really list of information, and which is based on well-defined perturbative calculations with proper resummations. So this is a summary of some. I mean, I spent just a few minutes to discuss this issue. It is much richer actually, but it is not the main purpose of this lecture. So here I leave you a list of references where you can find more details. This is for a general introduction on HeavyFlavor production. This is a description of the most used tools in the community to calculate the PQCD production of HeavyFlavor in hadronic collisions, which are this is an event generator, POWEG, and this is simply an automated calculation for the single particle spectrum. And for a systematic comparison of different, let us say, automated PQCD tools, you can have a look at this reference, okay? And then, which are the final observables which are experimentally accessible, because clearly you don't measure quark, so you measure hadrons, so you can measure either D and B mesons, or also charmed and beauty baryons. Then you can measure a non-prompt J psi, so it means the J psi which comes from the decay of a B meson, or you can measure heavy flavor coming from the semi-leptonic decays of charm and B meson, okay, in which essentially they are decays mediated by weak interaction. So you have an C, you have an anti-quark, and this C will radiate a W, which, for instance, can decay in electron. Okay, then it can be either E minus or E plus. Okay, clearly. So and so at the end, what you measure are these, or even clearly muons and muon neutrino. Okay. Or you can even reconstruct jets which were originated by a mu meson. So you reconstruct a jet. Within this jet, you are able to see from the decay products that the jet was originated by a B quark. Okay, so this is another kind of observables. So first of all, it is important to check that if we want to study medium effects, that we are able to correctly reproduce the results in proton-proton collision. This is just an example of the results of these tools. So you see these are data obtained at, in proton-proton collision at 7 TeV in the center of mass at LHC. For D mesons, these are the experimental point. The green band is the uncertainty band, the systematic uncertainty band of the phone calculation, which is it is an automated tool for the evaluation of this single particle spectrum, okay, which I said several times it is equivalent, okay. And clearly this band comes from various reasons. From you have systematic uncertainties arising either from the value of the quark mass or from the value of the factorization and the renormalization scales. Okay, these are the main source of systematic uncertainties, so that you don't have a line but you have a band. And then the curves, okay, refers instead to this Monte Carlo implementation of next to leading order PQCD matrix elements interfaced with a Parton shower stage, okay, with different choices of the fragmentation function. And you see that the spectrum is quite well reproduced. This is another study in which we can try to simulate, for example, the fraction of electrons coming from the decays of beauty over the total number of electrons coming from the decays of charm and beauty. And you see these are the prediction of this kind of event generators, and these are the experimental data. Okay, and you can also try to measure correlations, azimuthal correlations between, for instance, a trigger D meson and the associated hadrons in the same event. So with the idea of to study somehow the QQ bar correlation, so not only the single particle distribution, but also so for each event how a quark is associated to its companion, which was produced in the same hard event. Okay, so essentially you have seen that we can be quite satisfied and say that our tools that we use to simulate the initial production of HeavyFlavor are quite well validated on top of experimental data, and both for what concerns tools for the calculation of this single particle spectrum, and for more flexible tools which provide you a more differential information on the final state, which are these event generator. Okay, so the difference is that as an output here you get really a list of particles for each event. As an output here you have a theoretical curve that then possibly you can use to generate particles following that distribution. Okay, but for instance here you lose any information on two particle correlations. Okay, because it is an integrated, it gives you an integrated information. So let us move to HeavyFlavor in heavy ion collisions. I will focus on displaying the conceptual setup, and I will show some results and comparison with the experimental data, and then maybe I will sketch, give some hint of possible future developments of more of the on the most recent also results. Okay, so this slide is just to give you some flavor of all the machinery that you must develop to perform a realistic calculation. Okay, let us start from the beginning. You must simulate the initial production, which is described by perturbative QCD, since you have this large mass which gives you a hard scale, and possibly supplemented by nuclear effects, because for instance the nuclear PDF, the Parton distribution function of a nucleo in a nucleus are not equal to the Parton distribution function of a isolated nucleon. And then you can also have also other non-perturbative effects, like this initial KT broadening in nuclear matter, in the sense that so this is a nucleus. If the hard event occurs here, I mean the incoming parton has transferred this, before the hard event has transferred this length of nuclear matter, in which it can have exchange some momentum, and so it can have acquired some transverse momentum broadening also. Okay. Then you must have a description of the background medium in which the heavy quark will propagate. So it means having information on the temperature and also on the fluid velocity of this medium. Okay, and from the temperature you must also get information on the transport coefficient of the medium. We will see later on why this. Then you must model the interaction of HeavyFlavor in the medium, and you must also model hadronization in the presence of a medium. Because I mean, in the vacuum usually hadronization is modeled by simply fragmentation functions which were tuned to reproduce data in E+ E- collisions. And in the vacuum actually the process that you can imagine to happen is that you have some high energy parton with still some virtuality, which for instance can radiate a gluon. This gluon can split into a q-cubar pair, and then this could be a color singlet object, and then it will give rise to the hadron that you measure at the end, and which will have this high energy parton as his transparent, okay? But actually, I mean, this is what happens in the vacuum. In the medium, since this parton will propagate in an environment in which it is surrounded by a lot of other colored particles, it can also recombine with some of these thermal partons, okay? So clearly this is not something well under control. It is not even under a good control in the vacuum. There is a lot of cooking in the models which describe hadronization. This issue of medium hadronization can be considered an item of interest in itself. Like for instance, you can be interested in studying changes in the hadrochemistry in nucleus-nucleus collision. So for instance, you can check whether in nucleus-nucleus collisions you produce more ds or more lambda c mesons, hadrons with respect to proton-proton collisions. But I mean, at the same time, so clearly this can be something of interest, but at the same time, if your main focus is to understand the interaction of the heavy quarks with the medium, and so to extract information on the medium in the confined phase, this can be also considered a source of systematic uncertainties, since we will see at the end that depending on how you model hadronization, you can get a really different result for the final observables, okay? And then clearly you must model the final decays into the particle that you measure. And clearly, ideally, only this stage should be, let us say, model dependent, in the sense that I mean, clearly only this is ideally only this one is the point in which the procedures adopted by different groups trying to face this observable should differ. Actually, since you see this is a multi-step setup, each of these stages, different group doing research in this field can decide to adopt some particular assumptions and simplified picture, and so at the end it is also difficult to have a clear apple-to-apple comparison of the results of the different groups, okay? Okay, so let us remind for a moment which is the conceptual setup which we are working. So we've seen that the description of soft observable is based on hydrodynamics. We had some lectures on hydrodynamics. It means that in this case we are assuming to deal with a system close to local thermal equilibrium, and no matter why it reached such a stage, okay? Clearly, modeling how it reached such a state, it's a challenge, but you can also take it as a working assumption, okay? Then the description of jet quenching, which we also studied in these lectures, is based on a picture of energy degradation of external probes like IPT partons, which propagate in the medium. The description of HeavyFlavor observable is something peculiar, somehow in between, because it requires to develop a setup which is given by transport calculations, allowing one to deal with a more general situation in which, in particular, to describe how particles asymptotically would approach thermal equilibrium, okay? So it's not that okay, the system is close to thermal equilibrium and I follow its evolution. No, I want really to describe how particles asymptotically tend to thermalize with the system in which they propagate. Now, clearly, all these considerations depends also on the kinematic region which I'm looking at, because at IPT, so for very energetic HeavyFlavor particles, HeavyFlavor study are not longer really related to the issue of thermalization, but can be rather used as a tool to study the mass and color charge dependence of jet quenching. Okay, because for instance, if I measure a very high energetic B meson in the final state, I'm sure that this B meson comes from a parent B quark, and so of the B quark I know the charge, I know the mass, and so I know exactly which was the particle propagating in the medium. Okay, because if I measure a high energetic pion in the final state, this pion can come from the fragmentation of whatever partons, either a gluon or a quark. Okay, but we will not focus on this issue in this lecture. So why charm and beauty are considered heavy? Well, of course, due to their mass, but so their mass is big, but it is big with respect to what other scale. So their mass is, first of all, is much bigger than lambda QCD, so that their initial production is well described by perturbative QCD. But secondly, their mass is also much larger than the temperature of the medium. So we have a mass for the charm around 1.5 GeV, and the temperature of the medium, which at the beginning can be in the most central region around 400 MeV. And for the beauty, right, we have a mass of around 4.8 GeV. So the thermal abundance in the plasma would be negligible, and the final multiplicity measured in the experiments, in which I have an expanding fireball with a limited lifetime, is entirely set by the initial output production. At least this is what we expect. And then finally, the mass is also much larger than GT, where GT is the typical momentum exchange in the collision with the plasma particles. And this means that I need many soft scatterings to change significantly the trajectory of a heavy quark. And we will see that we will strongly rely on this assumption to develop some theoretical tool to describe the propagation of the heavy quarks. So for realistic temperatures, actually G is of order 2, so that one can wonder whether charm is really heavy. And we will also compare results of the setup both for charm and beauty, okay, and check how restrictive is this assumption. Okay, this was the introduction. Now let us try really to understand how it is possible to develop a transport setup. So we start from the Boltzmann equation that we have already seen a few times during this class. So it's an evolution equation for the heavy quark phase space distribution. Again, we are considering heavy quark as a classical on-shell particles, of which we can know exactly both the position and the momentum. And the Boltzmann equation essentially tell us that the total time derivative of this phase space distribution is given by a collision integral, so a balance between gain and loss processes. Okay, where this total derivative is a total derivative along the particle trajectory, so it is given by a partial derivative with respect to time, a gradient with respect to space times the velocity, plus a gradient with respect to the momentum times the force due to possible mean fields present in the medium. Actually, in the following we will neglect this term, and in order to develop the setup, we will also consider the case of a uniform medium in which these special gradients are negligible, completely neglected. So the only contribution to the evolution of the phase space distribution is given by collisions, where again collision integral, written explicitly here, is given by this balance between gain and loss processes. For instance, in the gain process, I start with a quark which had a momentum different from P, and due to the collision, at the end this is the rate of collision in which I exchange with the medium momentum k, I'm left with momentum p, and vice versa in the loss term. I start with a quark with momentum p, but it can exchange momentum with the medium or momentum k, and being found with a different momentum in the final state. So this is a loss contribution. Okay. Now the Boltzmann equation ensures the fact that asymptotically I reach thermal equilibrium with the medium. Why? Well, let us check and let us consider the situation of having a gas of classical particles, so obeying Boltzmann statistics and with no Pauli blocking and Bose enhancement factors. Okay. So write more explicitly the gain and loss term, writing explicitly also the distribution function of the particles with which I interact. Okay, and so in this case I start with a heavy flavor with momentum p prime, which it interacts with a medium particle with momentum p1 prime, and I have this transition rate to get particles with momentum p and p1 in the final state, minus vice versa a loss contribution. Okay. Now the point is that in the case of time reversal symmetry, these two transition rates are the same. Okay, and so I am left with this expression for the collision integral. Then I want to check when I reach the stationary limit. So when this collision integral is 0, it means that I have an exact balance between gain and loss processes. And this exact balance, well, of course, trivially, is there when this transition rate is 0. It means that I have just free streaming and no gain and no loss term. But this collision integral is 0 also in another situation in which this transition rate is non-zero, but what is 0 is the quantity within the brackets. And so if I assume, so for the quantity within the brackets, I must have this condition supplemented clearly by the energy conservation. And you see that if I start with a medium particle obeying this thermal distribution, the only condition to fulfill this, the only possibility to fulfill this condition is to have an exponential distribution also of my heavy flavor particles, which so asymptotically heavy flavor particles should relax to a Boltzmann distribution corresponding to the same temperature of the medium particles. Okay. And this is a general result. This is, I think you can find it in the first pages of the Landau book on kinetic theory. So, however, the Boltzmann equation is a difficult equation to solve because you see it is an integral differential equation. Okay, so the quantity which you differentiate is contained inside an integral in the right hand side. So you want to simplify somehow. And a possible simplification is the one suggested by Landau, and so it is the simplification of expanding this collision integral for soft momentum exchange. Okay. Clearly, if you expand for soft momentum exchange, the zero order term cancel, and you're left with the first and second order term from the expansion of this. Okay. And so you are left with this Fokker-Planck equation, which are expressed in terms of this quantity. So they are given by the first and the second moments of the transition rate. And in the case of isotropic medium, clearly the only possibility to build a correct tensor structure for this object is to factor out a dependence on pi and a dependence on these longitudinal and transverse projectors. Okay, so at the end, your Fokker-Planck equation is expressed simply in terms of these three transport coefficients. Okay, which are scalar functions, which in general can also have a dependence on the particle momentum. So the problem is reduced to the evaluation of these three transport coefficients, which in principle can be directly derived from the scattering matrix. Okay. Now, actually, now we must check how the approach to equilibrium take place within this approach, because I mean, in the Boltzmann equation we have seen that it is guaranteed. In the Fokker-Planck equation, this is no longer the case, because in any case we are not solving exactly the Boltzmann equation. We are solving a simplified version of it. Okay, so but we want to be sure that I mean, if our approximation has to make sense, we want to be sure that our approximation, in any case, ensure that particles asymptotically reach thermal equilibrium. Otherwise, we have built an approximation which makes no sense, because it doesn't drives the system to thermal equilibrium, which is what happens in nature. So notice that the Fokker-Planck equation can be viewed as a continuity equation for this probability current, let us say. Okay, so of course where now the only difference is that here I don't have a divergence with respect to x, but I have a divergence with respect to p, to the particle momentum. Okay, so I can wonder when an equilibrium distribution is a steady solution of this equation, and a sufficient condition to have this is that this current vanishes. So if this current vanishes, in the right hand side I have 0, and I have that this is a steady solution. Okay, so what I have to do is to substitute this equilibrium distribution here and check when this quantity within the brackets vanishes. Okay, and it vanishes once this is equal to this right hand side, because here notice that I have to derive I notice that I have a momentum here. I must take the derivative with respect to the component j of the momentum, but this momentum dependence is contained both here and here. Okay, so I can derive both. I must derive both. And so notice also that if once I have a derivative with respect to j of something, I can write it as a derivative with respect to p, where p is equal to square root of pi times the derivative of p with respect to pj. Now this, if we do this, the derivative of p with respect to pj, what do I get? I get 1 over 2 square root pi times 2 pj. So what I get is pj verse. Okay, check that I am doing things correctly. So I can write it as, okay, Now you see that, for instance, if you do this kind of trick, you can reduce this expression to this, okay? Because of course you must also take, for instance, here where this term comes from. These terms come from the following. I have a minus bij times this derivative of f(ec) divided by pj. So I can write it as the f(ec) over dep over dp times dp over the pj. So this this provides you a factor -1 over t. This provides me a factor p over ep, okay? If you see, they take a derivative with respect to p, you get p over ip, and this provides me a factor pj. Now, which is the tensor structure of this? The tensor structure of this is pi pj times the coefficient b1 plus delta ij minus pi pj times the coefficient which I think I have called b0. Now you see that since this is now contracted with this, this transverse contribution cancel, because this is pj, which is contracted with the projector in the direction transverse to pj, so this term is 0. This pj contracted with pj gives 1, and I am left with this, okay? And so this is the origin of this term, okay? Which is here. Well, probably I think there is, I have forgot a factor pi overall, but you can you see, because now I'm left with p dot pi versor, which is pi, okay? So in this formula there is a factor, a term pi missing, okay? And then so we have correctly treated this part. Then we are left with the necessity of deriving with respect to pj this tensor, and you can express this tensor again. You see here you find delta ij minus pi pj times b0. I just recasted everything in this form, plus this. And where now, once you take the derivative with respect to pj, here you have just to derive b0, okay? And with respect to pi, because there is the delta ij. Here again, once you take the derivative, you must take the derivative both with respect to p, but also you must take the derivative of this structure, okay? And if you do everything correctly, you are left with this result, where d is the number of space dimensions. So in our space, d is equal to 3, okay? And this number d comes just from the derivative of pj of this term, okay? Because clearly, if I is equal to j, you get either I equal to j. I mean, once you derive this with respect to this, since this j is summed, you get a factor 3 over the number of special dimensions. Okay, so at the end you get this, and with this relation is called Einstein fluctuation dissipation relation. And why it is called like this? Because it is a relation which ensures the fact that your Fokker-Planck approach is able to describe the approach of the system to thermal equilibrium. Fluctuation dissipation relation because it connects a fluctuations, because these are momentum fluctuations along the longitudinal or transverse directions, with a dissipative effect, because you see in the Fokker-Planck equation this plays the role of a dissipative force, or a friction force, and this will play the role of describing momentum fluctuation. But we will see later better explicitly this. Okay, notice that if you don't have any momentum dependence of your coefficients, clearly all this derivative is 0, and also you have no distinction between transverse and longitudinal if you don't have a momentum dependence, so that also this term is a 0. So in the limit of neglecting the momentum dependence, which is the non-relativistic limit, you get A is equal to b1 over t times in the non-relativistic limit m, which was the relation original derived by Einstein in his study of the Brownian motion. Okay, so in fact this is called Einstein relation. So let us ignore, as I was saying, the momentum dependence, and call this coefficient gamma, and these two coefficients let us call d. So actually in this limit I decide to call this gamma and this d. So the Fokker-Planck equation reduces to this equation, and as an initial condition let us start from having all particles with the momentum p0, and let us follow their evolution. You can check that this expression is a solution of the equation which satisfies this initial condition. Okay, asymptotically, so for t to infinite, the solution forgets about the initial condition and reduces to this expression. That, okay, if you identify this with an inverse temperature, this is a Maxwell distribution. Okay, so 1 over t equal to gamma mq divided by d, and you see that you recover the equation that I wrote previously. Gamma is equal to d over t mq. Okay, you had already seen this kind of stuff sometimes. Okay, so this I skip. This is clearly the final result in the three-dimensional case. So this. Okay. So let us interpret now physically these two coefficients, gamma and d. So the interpretation comes, this is a distribution. Let us consider its first two moments. So the moment of order 1 and the moment of order 2. So let us, these are actually the cumulants of this distribution. And you can verify trivially, just performing this change, this manipulation inside the integral of this distribution, that that you get these results. Clearly, let us for instance focus on the first moment. You see that if I imagine to integrate this with respect to this distribution, clearly here I would have an odd moment of a Gaussian, so I would get a 0, and this would, I would just get this because the Gaussian is normalized to 1. Okay, so you see that asymptotically I forget of the initial condition, and asymptotically the expectation value of the momentum along each direction goes to 0. And for but however I have a width of this distribution, so that its second order cumulant leads to this result. If I take the T20 limit, I get this diffusive behavior. So this is why D is called momentum diffusion coefficient. Okay, and this is why gamma is called the friction coefficient. Okay, so this is was just motivated by the necessity of making you understand the setup. Actually, the situation is more complex because heavy quarks can be, in general, are relativistic. Heavy quarks that I produce in heavy ion collision, so that, for instance, I cannot neglect the momentum dependence and get this very simple formulas. Then clearly the dynamics must be interfaced with the initial after production. So I want to have a tool which is capable of taking the output of some QCD event generator and make this particle evolve in the medium. So not evolving a distribution, but really evolve event by event the particles that I produced. And then this dynamics does not undergoes in a static medium like what we did so far, but it undergoes, it takes place in a medium which undergoes an hydrodynamic expansion. So I need a generalization of this tool, and this generalization is given by the relativistic Langevin equation. So we will see that the Langevin equation is just a way of rephrasing the Fokker-Planck equation, but I mean, you know, it is necessary to do some step to check this. So the Langevin equation is a stochastic differential equation which essentially provides you a recipe to update in the elementary time step delta t the three momentum components of a quark which propagates in the medium, and this update is given by the sum of a deterministic friction force. It's the usual form, minus a friction terms times the momentum of the particle, plus a stochastic noise term. And this noise term has some property. Its expectation value is 0. Its strength given by its temporal correlation is characterized by being local in time. And if I write this tensor structure in terms of these two transport coefficients, I mean its strength is described by these two transport coefficients. We will see that these transport coefficients are closely related to the transport coefficient of the Fokker-Planck equation. Okay. So I need to calculate this transport coefficient, and then I am able to solve this equation. In the following, we will establish the link between these three transport coefficients and the transport coefficient that we saw before in the context of the Fokker-Planck equation. Notice that in particular the momentum dependence of the noise term requires some care, because you see that this B, this tensor which gives me the strength of the noise, is a momentum dependence. Okay. It is called multiplicative noise in the language of stochastic differential equation, and so one must treat this term with some care. So, which is the strategy? The strategy is to introduce this other tensor, which is very similar to b, except that here I have the square root of KL and KPerp. We redefine the noise variable, so before the noise was this xi, and it obeyed these relations. Now I absorb this tensor Cij in the definition of xi, and now I have a new, let us say, dimensionless noise variable zeta, which has more or less the same properties. Its expectation value is 0, and its temporal its correlations are local in time, but at variance with respect to the notation used before, they are also diagonal in space. And so you see that they are diagonal in space now because they have absorbed the non-trivial structure in the definition of the noise variable. Okay. So if you substitute, instead of having this expression with this new definition of the noise variable, I have this expression. Where notice that the particular point is that since this strength, this tensor, which encodes the strength of the noise as a momentum dependence, I have some freedom in choosing where to evaluate it. So in principle, I can evaluate this tensor in any time, in any point in the interval between time t and time t plus delta t. Okay, so I can fix this xi as being any number between 0 and 1. Okay, depending on the value of xi, I will have a different discretization scheme. In the following, we will work in the scheme which is called Ito pre-point scheme, in which xi is equal to 0. Okay, but other schemes are possible. Okay. So now I want to establish a mapping between Langevin and Fokker-Planck, and the show which is the relation, and also in particular to show that they are equivalent, and show the relation between the transport coefficients. Okay, in the two equations. So consider an arbitrary function of the heavy quark momentum, g of p, and take the expectation value over the thermal ensemble, and consider its variation. Consider the expectation value of its variation within the time step delta t. And in this expansion, clearly I can perform a series expansion of this function, and I decide to stop at order delta t. Okay, so I will keep only in this expansion only terms which are of order delta t, so I will neglect higher order terms, and I will also keep only terms which, once I take an expectation value of a thermal ensemble, gives a non-vanishing result. Because, for instance, terms which contains a single factor of the noise vanish because the expectation value of the noise is 0. Okay? So remember that from the Langevin equation, this delta pi is updated according to the following algorithm. Okay, so you have a term of order delta t and a term of order square root of delta t. Okay, so for instance, here this term is quite easy, because if this is delta p square, from this I can only take the term of order square root of delta t, because everything else would be higher order. So you see that this is very easy to evaluate. So I simply I get a factor c from each of this delta p. Then in principle I could have c I k xi k c j l sorry zeta L, but since the expectation value of zeta k and zeta L is equal to delta KL, at the end I get a structure CIK CJK. Okay. Now the situation for the term of order delta p is a bit more subtle, because of course I have this term which is of order delta t, and which contains no power of noise, so it is non-zero and of order delta t, and I write it. Then of course in principle I could have also this term which is of order square root of delta t, but I mean it will contain an expectation value of a single power of the noise, so it will be 0. But notice that here I have the freedom to evaluate this term at any point. So I have also a contribution coming from the derivative with respect to p of this times xi times delta p, where now this delta p again, and this further delta p, where does this further delta p get a contribution? Well, of course it can get a contribution from here, but the point is that this contribution will be of higher order in delta t. It would be delta t over to the 3/2. So this further term delta p can also only gets contribution from the noise term, and so I have a further factor c. Okay, and then I have also again a contraction of these two indices for the same reason, because in principle they can be different, but since I must also take the expectation value of the noise of two noise variables, these are diagonal in space, and so these indices are contracted. Okay. So clearly you have written this. If you now divide by delta t, you have evaluated the time derivative of this expectation value. Okay, where this expectation value is evaluated according to this distribution function, which has a momentum dependence. Okay, so this expectation value, it will change with time. Okay, now the point is that now you can, in order to do the mapping, you can decide to evaluate this time derivative within another approach, so not starting from the Langevin equation, but starting from the Fokker-Planck equation, and then you will match the two results. Okay, so you rather than doing like we did in this slide, you will proceed by taking the time derivative of this object by considering the time evolution of the phase space distribution, and you evolve this phase space distribution according to the Fokker-Planck equation. Okay, so the time derivative, I have this. I evaluate the left hand side as before, so with the Langevin equation. Okay, so writing explicitly this expectation value in terms of this phase space distribution. Okay, it's what I did here. Okay, and just taking some integration by part. Okay, but this comes from the the slide, the previous slide. Then the right hand side I will evaluate with the Fokker-Planck equation, so in terms of A, I, and Bij. Okay, if you match now the two results, you can identify this AI with this term and this Bij with this other term, and this allows you so to identify these objects. So notice that here you see explicitly that independently from the discretization scheme, this KL and Kperp entering into the Langevin equation modulo a factor of 2 coincides with the B1 and B0 transport coefficient which enter in the Fokker-Planck equation. Okay, and this does not depend on the scheme. For the friction term, the situation is a bit more tricky, since you see that you have a dependence on the discretization scheme. Okay, so this is the relation between the AOP coming from the Fokker-Planck equation and the friction term, which you must actually insert into the Langevin equation. Okay, here I have simply written explicitly this derivative. Okay, but actually what people do more often is to work in the Ito pre-point scheme, in which this factor psi is equal to 0, so that the two objects coincide. So the friction term, the friction coefficient in the Langevin equation coincide with the friction coefficient in the Fokker-Planck equation, and is given by this Einstein fluctuation dissipation relation. Okay, and this is a check. Here you can check that actually the algorithm is able to describe the approach to thermal equilibrium. This is a situation, this is a test that we did by starting with a sample of some few millions of quarks, all the quarks with the same initial momentum P0, and then we let the system evolve, and depending on how large the transport coefficients are, you see that after a few Fermi over C, you go on top of an equilibrium relativistic Maxwell distribution. Okay, so the algorithm is able to describe the approach to thermal equilibrium. And maybe we can stop for 2 or 3 minutes. Okay. So we have developed the setup that we will use in our phenomenological studies, and now I will non si sente.